And it is my great pleasure to announce our first speaker, Professor George Shimizu from Canada. He's professor at the University of Calgary and interested, for example, in proton conduction and in carbon capture. And he's going to tell us as a keynote speaker about de-risking a MOF for practical carbon capture. Please, the floor is yours.
First of all, let me thank Stefan and the organizing committee for the chance to speak here, and the wonderful organization so far. For me, this audience, I'm looking around the room, and I don't think I've ever given a talk with so many people in the room whose papers I've been inspired by and whose work I've admired for a long time. So I'm really happy to be able to tell a bit of this story. Some of you may have seen Stefan Marks of BASF gave an excellent presentation on this topic this morning. And I think my talk is a complement to that because Stefan really presented it from the perspective of the big company. And I will present it from the perspective of someone who grew a crystal and thought, hey, I wonder if this can actually do something useful. Okay, so the compound I'll be talking about, which was very generously mentioned by Professor Yagi in his plenary, is one called CAF20. And we first made that over a decade ago, and we published it in 2021. And presently, it is part of a demonstration by a Canadian company called Svante, and they have been capturing 1 ton of carbon dioxide per day at a small capture facility in Vancouver, Canada. So that's basically where we'll end up. And so I really wanted to, many times when I have a chance for a casual conversation with people, they'll ask questions maybe they don't want to ask in front of an entire auditorium, more candid comments. So I've really tried to make this talk today to address some of those features. But I don't want to assume that anyone has read the paper or looked at it. So I'll just say CAF20, zinc 124 triisolate oxalate, first made in my group by now Professor Adsorption, Ramanathan Vaidyanathan. First crystallized in my group by Dr. Jan Binalin, who is the crystallographer at Memorial University. The main feature of CAF20, I would say, is that there is no strikingly important feature that would seem to dictate great carbon capture. A lot of the thinking in the literature over the past decade, I think there's been ebbs and flows of, you must have a polarizing functional group, you must have an amine group, you must have an open metal site. This has none of those. It's simply dispersive interactions, and the pore size ends up being quite special into how it works. Here's the obligatory set of temperature-dependent nitrogen and CO2 isotherms. Heat of adsorption here, the isotherms, actually, if you compare them to zeolite 13X, you can almost overtrace at the different temperatures. The heat of adsorption is bang on for zeolite 13X, and a lot of the working capacity data, everything is very comparable. And for MOFs, these are good. This is when we made this compound actually for the first time, it had the highest CO2 uptake that we'd ever measured in my lab. But at the same time, we didn't actually know the crystal structure. So that's a small but not insignificant takeaway, that you don't need the crystal structure to run the CO2 isotherm. Okay. So how do you move forward? You have a crystal, and you have a crystal structure, and you have isotherms you think are pretty good. And I've naively done this, where you go to someone, you see their business card, and their job title is greenhouse gas mitigation, perhaps for a very, very large company. And you say, oh boy, have I got a compound you need to know. I have a carbon capture. I have a solution for carbon capture. And the person looks at you, and in their mind, what they're thinking, oh, so sorry, you extol, of course, the crystal structure, the pore size, what we do in all of our MOF papers. And of course, you have good gas absorption data. But what the person is really thinking is you're going to bring them this on a skid. And you're going to not just bring this on a skid, you're going to bring a fate for the carbon dioxide. So in addition to bringing the entire carbon capture system, you're bringing a pipeline to dispose of CO2 that's been captured. That's what their job description calls for, okay? And they have a completely different set of metrics by which they will gauge success. Heat of adsorption has to become energy consumption. Gas capacity and selectivity must become purity, recovery, and productivity. So how do you go from these molecular features, atomic level features, through to data that's actually meaningful for this end user? And so a key point here is that all these metrics are important at the molecular level, but then they are a function of the specific process into which the compound is incorporated. Is it a pressure swing? Is it a temperature swing? Is it a vacuum swing? Some combination at whatever temperature as well, okay? And only then can you get to those. So a key step in between all that is the structuring of the powder. And so structuring refers to basically making beads, extruded pellets. Could be a laminate, could be something 3D printed. But why do you have to do this? So minimally, so you can do a dynamic column breakthrough experiment. If you just put powder into a column, it's just too much back pressure and you can't do the experiment, okay? But ultimately, what this needs to do is it has to give you the optimum complex fluid dynamics for your compound to be most efficiently used in terms of the mass transfer and the heat transfer. And there is no single magic recipe for that. That has to be done as a function of the gas stream you're treating, and it has to be done as a function of whether it's a pressure, temperature, vacuum swing. So completely integrated with the process. And if that sounds like a lot, it's a lot. That's what I just said is years of research, not for a person, it's years of research for a team, okay? So this gap in between structuring and a demonstration is probably the most significant gap on this figure. So how do you go about bridging that gap? Let me just say I'm very, very happy the conference, how many talks I've seen addressing this type of feature, okay? Addressing the structuring and really doing meaningful separation experiments. To do this optimally is asking a lot, and part of the reason for that is the company that is the end emitter in most cases is not going to share the process conditions that you need to target. Okay, so it's really a gap in many ways. Okay, so a question, what is the scale of a meaningful study or investment if you want to try to bridge that gap? I've asked this question of numerous people who are at this end of the problem. And what seems to be a consensus is if it doesn't capture at least 10,000 tons per year, it is not worth building. Now, 10,000 tons per year, if this is your problem, 10,000 tons per year is not a big facility. Okay, that's 30 tons per day. So that seems to be the low end of what you could be demonstrated at. Coming from the small end then, I've asked them, well, how big do we need to get for this to be meaningful for you? Zero length chromatography is not going to extrapolate to something that someone's going to model an entire plant's performance based off of. But as a first step, if you can do 1 kilogram, dynamic column breakthrough data on a kilogram data can be compelling for people. That can be meaningfully extrapolated. And again, that's not a hard rule. It's just what I've heard from most of the people that I've talked to. Okay, and if you think, well, a kilogram is a lot for a MOF, again, if you're asking for a team of people to potentially invest an entire team to invest months, years, and hundreds of thousands of dollars. Being able to provide data based on a kilogram shouldn't be prohibitive, okay? So with that in mind, I'll talk about de-risking. And I think de-risking is the key word here, because we're not demonstrating. We're just trying to make it easier for other people to use the compound. So of course, we have crystal structure, we have the gas absorption isotherms, we did the water isotherms. And a very unusual feature with CAF20 was that in contrast to zeolite 13X, 13X by, 13X is over 15 on the y-axis here. We actually show some hydrophobic behavior. So of course, the water isotherm being hydrophobic doesn't mean you're going to physisorb CO2 in the presence of water. There's 157 degrees difference in boiling points. But again, de-risking, let's show it's thermally stable. So here's 50 cycles showing retention of CO2 capacity. This is just an experiment that can be done on any TGA, just flipping between CO2 and carrier gas. We treated our compound with steam for a week, showed the PXRDs and the gas absorption isotherms were reproducible, set up a little rig to make wet acid gases and hit the compounds with that. And everything was looking good. So with this, so I will say at this point, Svante had already become interested in this compound. I think the steam experiment was really key. But we were also able to engage other collaborators with infrastructure that we didn't have. And a very important collaboration we developed was with the University of Alberta. So Professor Arvind Rajendran, he's like one of the associate editors for the journal Adsorption, but he has a home-built breakthrough rig. And so he was very happy. So his student Ty is actually now graduated and he's employed. He went straight to work at Svante. So if you're not used to looking at breakthrough curves, this is a breakthrough curve just showing a light phase and a heavy phase. So here, light phase, nitrogen doesn't absorb well to the material, so it breaks through first, and then CO2 breaks through. And as you vary the concentration of the heavier phase, what you see is the heavier phase comes out later and later. And why that is important, the interesting part of a breakthrough curve is the part to the left of the curve. Because that area, if you factor that by the flow rate, that actually tells you the volume of the column that's occupied by that fluid phase. Okay, the side to the right just tells you how much has come out of the column. So when you go to more and more dilute concentrations, what you see is that the heavier phase breaks through later, showing that even though it is less concentrated, the column is retaining its absorptive capacity. So this is what you expect to see when you have high selectivity for one phase over the other, CO2 over nitrogen. And again, 13X would look pretty much exactly like that. So when you go to CO2 and water, and so this is now 13X, not CAF20, what you see is very similar profiles, only now water is the heavy phase and CO2 is the light phase. So again, this is consistent with heavily preferred adsorption of water over carbon dioxide. And this is why zeolite 13X isn't a great CO2 sorbent. When you go to the same experiment, but on CAF20, what you see is a completely different profile. What you see is that when the concentrations are varied, the CO2 breakthrough is very comparable, very similar times. And again, there's not a big variation in the water breakthrough or the CO2 up top and the water on the bottom. So this profile is very consistent with highly competitive absorption between CO2 and water, okay? A more compelling experiment is actually to do the water breakthrough. So this plot on the left here shows two experiments. The first one is just at 13% relative humidity, water breaking through CAF20. So in dimensionless time, you can see, what is that, about 5 it breaks through. When you switch the carrier gas to carbon dioxide, the water breaks through much, much sooner. Okay, so as you remember, the area to the left of that curve represents the volume of the column that's occupied by that fluid phase. So this entire region here represents the volume of that column that used to be occupied by water that is now occupied by carbon dioxide. And this is physisorptive, all right? So this plot on the left represents one data point on this curve. So the three curves on the right here that we're looking at, green is the water uptake of CAF20, red is the CO2 uptake of CAF20. The blue curve is the most important one. The blue curve is the water uptake of CAF20 in the presence of carbon dioxide. Okay, so there is not only the retention of the carbon dioxide capacity, there is actually suppression of water physisorption by carbon dioxide. And that is because of the unique pore structure of this compound, because of its reticular nature, okay? And so again, every one of these, this plot on the right represents almost a year of work for Ty, right? As far as the water suppression, this may be something that is observed in other compounds. Honestly, the experiment isn't done as commonly as it probably should be, all right? And it's not an easy experiment to do. I was asked once why CAF20 wasn't identified by many of the machine learning studies that were predicting good MOFs for CO2 capture. To actually realize the full benefit of the material, you would have had to have considered the competitive water CO2 experiment, okay? This observation was correlated by longtime collaborator Tom Wu, that basically showed that at low humidity, CO2 actually has a higher heat of absorption than water in this compound. Okay? And of course, as you go to higher and higher degrees of humidity, water attracts water, and water gets a higher heat of absorption. Right. So with that, let's move on to the merging to engineering. So this is a Canadian company that's been around for about a decade, Svante. And so Svante has two proprietary technologies that are tremendously valuable for people making powders. And the first is that they know how to do structuring. They do structuring very well. And the way they structure is they take a sheet. Well, I'll talk first about the mechanical engineering. Their system consists of a bed of solid sorbent. It doesn't have to be a MOF. They've looked at carbons, they've looked at amine modified silicas, but it's this thing that looks like a cheesecake in the middle. This is a rotating wheel. In their process, flue gas comes in, the CO2 is trapped, the wheel turns. Where their process is really unique is direct contact of steam to remove the carbon dioxide. So then you separate the CO2 from the steam. This is not mixed with air. There is no carrier. It's just hot H2O molecules. At that point, then the bed is dried and the capture can begin again. In order to do this quickly, so really it's referred to as a rapid temperature swing, but it also has a component of concentration swing here. You're really flushing the bed with hot water. The other proprietary bit that Svante has is how they do their structuring. And so they take a carbon mesh and they'll coat the sorbent powder onto it. And so that's one of the variables, is how thick is that coating. But then onto that, they will print dots of silica, and the dots of silica separate the sheets. And so this gives you control over your mass transfer and your heat transfer. And so there is a lot of option to tune how this is carried out. So for Svante then, it's not like they were going to go, let's go build a 30 ton per day facility. Obviously they need to know they're not wasting their time with this compound. So they took just the powder and exposed it to 7 days direct exposure to flue gas. And this is the flue gas composition that they were looking at. And again, the compound lost less than 2% of its CO2 uptake. They then took one of the laminates. So this is a slightly higher test because you're no longer testing just the powder. You're actually looking at its adhesion and how it stays as the sheet. And they have a little rig that it looks like a little telephone book with a window in it. And they put in one sheet and they blast it with 1 second of steam followed by 4 seconds of hot air. So it's a 5-second cycle, and they let this run for 24 days. So this is 450,000 steam hot air regeneration cycles. And during that test, the compound lost 1.6% of its CO2 capacity. So that is meant to simulate a couple years in the field as far as the steam regeneration. And here's Svante's absorbent expert, Omid, and their vice president of research, Pierre. Okay, so beyond the steam stability, there's the actual drying step, right? So the drying step is with hot air. And so you need high oxidative stability. And this is just showing, again, that CAF20 didn't lose anything in that step. But as a comparison, this is an amine modified silica. And the y-axis here is percent of the normal uptake. So the original amine would have a higher working capacity than the CAF20, but basically it loses almost 90% of its capacity with the amine oxidation. Okay, so again, if you want to compare working capacities, my question would be, well, which cycle should we draw? In December 2020, I was very happy in December 2020 because it was the first time that Svante actually publicly said that they were looking at our compound, even though it had been a few years. And so in Global Cement magazine, they did an interview and they talked about a partnership with cement industry, Lafarge Holcim. And so it said, how long did it take to develop the MOF sorbent? And it said the MOF known as CAF20 developed University of Calgary. We knew relatively early on that it was what we needed. The cost was too high. In 2018, the researchers found a different way to make it. So even to try to make a kilogram in 23 mil autoclaves, and we did that. You know, you need at least 50 of them to go through, right? It's not scalable. But a lot of variables, and you know, Stefan, if you have questions about this, Stefan Marks is here. And it isn't just about can you make the compound, it's can you isolate the compound and can you do it quickly? So a lot of things like we found things like ease of stirring, ease of filtration. Do you need to wash the compound? These were all big issues, but we found a way to make it at room temperature. And this is actually still about a week ago, a student made a 2.5 kilogram batch in the lab using this setup. And as inelegant as it may seem, I think in terms of it de-risking this for someone up the chain, part of it was to show we didn't need anything really fancy to do this. 2.5 kilograms, the slurry only fills to about here. We could put more in the bucket, but we couldn't stir it. And in our hands at room temperature, the limiting step is that when you make the compound, it still has maybe a little bit of oxalic acid, maybe a bit of triazole blocking the pores. And the limiting step is washing it. So inside here, there's something called a filter sock from the food industry. And it's just washed repeatedly. This is a filter to scrub the methanol that we're washing this with. But again, we're still using this and we can make 2.5 kilogram batches. So here's Stefan, and Svante contacted BASF, and they just took things to another level, and very, very quickly, they had 300 kilogram batches that would produce the same isotherms as we were getting on a 100 milligram scale. And again, this is, that was published in the paper from last year, but Stefan has carried this, it's almost at ton batches now, and it's also gotten much more green in terms of the actual conditions that are being used. So kudos to Stefan and BASF. So in terms of then, now that you can get your hands on many, many kilos of CAF20, I should say, as of right now, there's been about 8 tons of CAF20, 8 or 9 tons of CAF20 made so far. But at Svante, they do all their manufacturing. So this is coating the carbon mesh. This is printing of the silica dots. This is, they have a robot that will stack stack the sheets together, and then ultimately into the mechanical engineering rotary assembly. And again, when you're at that stage, you can look at different parameters. And so here is a 0.1 ton per day scale rotating assembly. And here, this is just so one thing I'll point out here, we're not talking absorbent capacity, we're not talking selectivity. Now the KPIs we're looking at, productivity, purity, and SR is steam ratio. And so what we see is that over the course of this experiment, which is 2,000 hours, the performance maintains the same. And this is with real flue gas. This is with real flue gas, actually simulated cement flue gas. When they say simulated cement flue gas, it means they take natural gas, flue gas, and they add carbon dioxide to it, because that's really what's happening. Except in the cement plant, the CO2 that's added is coming from the limestone heating. So then we have retention of these three parameters, and I think they were very happy that this test ran for 2,000 hours. So I will say, you notice there's no, the productivity number here is, I think, 10 kilograms per kilogram of sorbent. The actual number is not important. The key is that it's retained, because this, when we talk about optimizing or alignment with the process, the duration of the capture cycle here, the duration of the steam treatment, they're not optimized for CAF20. This is a set rig that every solid they look at goes into. Okay, so maybe the steam is being added before the bed is even saturated. Maybe there's much more steam being added than is necessary, which would certainly be the case for CAF20 compared to an amine modified chemisorbent. But the key point, retention of the KPIs for almost 2,100 hours. Now, this bed also has on the bottom an activated carbon guard that is there to scrub the NOx. But because the test had gone so well after 2,000 hours, they just removed the carbon guard to see how it was going. So even with the exposure to NOx with another 100 hours, the KPIs were retained. Okay. And so this is what a 30 ton per day pilot will look like. This will be later this year or next year. This is with Chevron down in California. This is for natural gas combustion, capture from a natural gas combustion project. And this would need about a ton of CAF20. So as I mentioned, presently this is working at a facility in Vancouver. And I've actually never, during COVID, I've never actually been able to go see this. And I've talked to people who've toured it. So one day I'd like to go and have a visit. And let me just say what I'm saying. Certainly this meeting, it's become very clear. I think people are understanding the gap that needs to be bridged. And these are just works that talk a lot more about, you can have a good material, but it's really important to integrate that with the optimum process. So a key takeaway here would be, there isn't a best material. There's a best material for a specific process, assuming it can be structured correctly, okay? So as far as the Svante system then, why is CAF20 a particularly good synergy? Well, it has everything you need for the capture step. When you go to the regeneration step, you want a modest heat of absorption for CO2, but it also has to be stable with steam. When you go to remove the water, you'd like the water to be easy to remove, and you'd like this to be oxidatively stable because you're blasting it out with air. And you want the whole thing to be fast and durable. And I'm just going to highlight these items in blue. And why am I hiding the items in blue? Everything there is important. The items in blue have nothing to do with the CO2 isotherm. Okay, so when I see papers that are just making definitive rankings of absorbance based on CO2 capacity or selectivity, it's such a small part of the picture. And I don't say that to criticize things that might have good CO2 capacity and selectivity. Of course, all else being equal, those are higher is better. But there may be good materials that are being overlooked because they aren't exceptional in those regards, but they may have everything else that's needed. Okay. Yeah, so with that, if I want to make one last point, that's, I think, is very important. The challenges in bridging this, one of the big ones, and maybe it's underappreciated, less valid comparisons. There was a funding call, and people would ask me, well, what does it cost to capture CO2 with your compound? And I would say, well, it depends on the process. So this agency decided that, all right, well, we'll benchmark versus monoethanolamine. So you have to provide an expectation of capture at 25 degrees, regeneration at 110 in a temperature swing process. And in that way, they felt they were benchmarking so that it was an apples to apples comparison. So to take a new technology and force it to be benchmarked versus the conditions that are optimized for the status quo, this is as far from an apples to apples comparison as you could possibly have. Okay, so you need to have your material benchmarked for the process conditions under which it is performing well, all right? So with that, I'm gonna just skip ahead and thank, I'd say it's been the privilege of my career to work with everybody on this paper from all these different agencies. And I'm absolutely thrilled. And again, I thank the other researchers in the room for all the inspiration over my 24-year career. And I'll thank my students. And I'll just end with a picture of, these are glaciers about 2.5 hours drive from Calgary. And you can go, and they benchmark the recession of the glaciers over the past decades from the highway. But also 2022, August, was the hottest month we've ever had in Calgary since they've been keeping records of temperature. And this is a photo taken 2 days ago, just showing the haze from the ever increasing forest fires we seem to be having nearby. So with that, thank you for your attention.
Thank you very much for a very inspiring lecture. We have time for one quick question.
So it was just beautiful work, and I see you're starting to scale this, but the real scale issue is so huge. I personally live in Wyoming now. Wyoming exports 1 million tons of coal a day, which produces more than 2 million tons of CO2 a day from burning it. Do you see any possibility that any carbon capture technology can be scaled just to take care of Wyoming's CO2?
So my answer has to be yes. I have always thought that this is something that could be doable. And I think the incentives are all going in the right directions, but it's steps, right? The cement plants are in one aspect lower fruit because they're about an 18% concentration stream without SOx. And again, that isn't the final solution. That's de-risking for someone else to invest in the next bigger project. So the de-risking is ongoing.
Thank you very much again for this great talk.